over some of them. And, I mean, I may cover the same material, but I never do it the same way twice. Okay. My chapter 11, your chapter 13 in Brown. We're going to talk about properties of solutions. We know that a solution is a homogeneous mixture. I think we've covered that last semester. Yeah. And it can be any phase. Any two or more phases can combine into a homogeneous mixture. Gases, of course, if you combine two or more gases, they're always a solution, every time. Examples of liquid-liquid solution is booze or antifreeze. Brass is an example of a solid, two solids in solution. The only way they can get there, of course, is you have to melt them together, and then they re-solidify. Now you have a solid solution. Gas in water, carbonated water is an example of a solution. Sugar water, seawater, those are what we normally think of as solutions. And that you can even have a solid and a gas as a solution. In your catalytic converter in your car, you have these little, used to be ceramic beads coated with platinum and palladium, but shade tree mechanics quickly figured out all you had to do was just punch a hole in the bottom, and they'd all fall out, and then you just braze over the hole, and you could run your car as if it didn't have that restriction on it. But the manufacturers figured that out, and now they make your catalytic converters with kind of a honeycomb ceramic coated with the platinum and palladium. So you can't do that anymore. But this example of hydrogen in platinum is a case of catalytic reaction. You've heard of partially hydrogenated vegetable oils? You haven't heard of that? They take vegetable oils that are, I forget the term now, unsaturated, polyunsaturated. They're the best for you. But they also have very low smoke point, so you can't heat them up very high. So for restaurants, they partially hydrogenate them. They stick hydrogens onto the double bonds. They open the double bonds and stick hydrogens onto them, and that makes them higher smoke points so that restaurants can use them in their fryers. Well, the way they do that is they take the oil and mix hydrogen with it and run it over platinum catalyst, and that accelerates the process. Well, in the process, hydrogen is attaching to the solid platinum, and that is, in fact, a solution, a gas on a solid. Okay, so we're going to look at these four ways to express solution composition. The most often used is molarity. Y'all use molarity in the lab?
Yeah.
Okay. So you already know that big M stands for molarity, and it's moles of solute per liter of solution. Did we already define what a solvent and a solute was?
Yeah.
Okay.
Online or on the...
Good. Okay. Now, this is great to use this one. If I have a solution that I say is exactly 10 molar, that means if I pull out a liter from a larger barrel of the stuff, then I know that I actually have 10 moles of the solute. That's the power of this method. And measuring volume is, well, actually, sometimes mass is easier to measure, but in some cases, volume is easier to measure. And when we measure out this much, or we could take out, and this is an intensive property. In other words, it doesn't matter how much you have, you still have that ratio. So if you have a small amount, it's 10 molar. If you have a big amount, it's 10 molar. The other method is mass percent. And this is, let's see, I would say percent mass mass. What that means is it's mass of the solute per mass of the solution. So this way, it's parts per hundred only in mass. So it would be like 1% would be 1 gram of 100 grams of solution. Okay. Mole fraction, that might be an odd one. And we use this big X letter. In Greek, that's called the chi. And this, if we say the mole fraction of A, means that we have moles of A per total mole. And that's going to be a value less than 1. I mean, if it's 1, that means you don't have a solution, because you've got all A. So if we have A and B mixed together, and we say mole fraction of A is 0.35, then automatically the mole fraction of B is 0.65. So it has to add up to 1. Molality, that's the one we're going to use next week with this procedure. Molality is a little m. And that means moles of solute per kilogram of solvent.
That's what we're gonna use for our lab?
Yeah, that's the one for our lab. Molality. Mm-hmm.
That's too close to molar.
I know.
They're not the same.
There's a big difference between capital M and little m. Now, the reason that we have to use this one for our lab is because we're measuring a difference in freezing point, temperature change. And temperature change affects volume. So if we use this one, that would be affected with the temperature change. It wouldn't be constant through the experiment. So we use this one because it's based upon mass of solvent. That doesn't change with temperature. That's why we have to use that one. We've got some more slides in here, and I've already talked about those. Molarity. Well, okay, examples. All right. I guess we can do these. It's like these methods of expressing concentration are like any algebraic expression. If I say molarity is this, moles per unit volume, then if I know 2 of those, I can solve for the third one. I just have to be sure that the units of measure are correct. This is going to be moles always, my little n. This one for molarity has to be in liters of solvent. So in this case, we have 1 mole of sugar. 0, 0. Yep. 1 mole of sucrose, I assume, and 125 milliliters of solution. That's not the right unit of measure. 125 milliliters is how many liters? Can you do that in your head?
Yeah.
0.125. Well, think of it this way. The unit of measure that you want is bigger than that, so the number has to get smaller. That tells you which way to move.
Yeah.
And the ratio is 1,000 to 1 million.
Yeah, I knew that.
Mm-hmm. Okay, so we have to put in 0.125 for our volume. Okay, 0.125 into 1 is what? I can't do that in my head today. 8. Let's see, 3 significant figures. 8.00 molar. There you go. That was a fairly easy one. In this case, we have a 10 molar sugar solution. So molarity, in this case, equals 10 molar. And other information we're given is what volume of this solution do we need for 2 moles of sugar? So we have this value in that position, and this is our unknown. So this one goes over here, and that one comes over here, and that's 2 divided by 10 is 2/10, 0.2. 0.0 liters would be the volume you would need. Now, most measuring devices in the lab are measured in milliliters. So how many milliliters would that be? 200 milliliters. All right. Another one. It's more and more complex. So we've got two solutions, and the point of this exercise is to emphasize the fact that mass depends upon the compound. Right? If you have 100 grams of both sodium hydroxide, you have 100 grams, and potassium chloride, I think the other one was, yeah, 100 grams. And you're going to put them both into a final volume of 250 milliliters. Then first question is, will they be the same molarity? No, because they're different molar masses. You got to convert these to moles before you can calculate the solution. So what we need is the conversion factor here that will convert grams into moles. And the sodium is what, 23? Yeah, 23. Oxygen is 16. Hydrogen is 1.01. So that's 40.01 there. So that's 100 divided by 40.01. That's 2.499 moles. Now we can calculate that in 250 milliliters of solution. So the molarity is going to be 2.499 moles. In 250 milliliters is how many liters? 0.250 liters. So that's rounded off actually to 4 significant digits. 1, 2, 3, 4. It'd be 9.998 molar. How about this one? Let's see, potassium is what? 39.10. And chlorine is 35.45. 5, 5, 14, 74.55 grams per mole. We'll divide 100 by that. 1.3414 moles. So the molarity of that solution is going to be less. 3414 divided by 0.250. 0.250. 5.366 molar. Okay. So we have the same mass, different molarity. Okay, they rounded it off to pretty significant figures. I don't know why, because we're allowed 4. 5.37. Okay, close enough. All right. That's molarity. Mass percent. Now we're talking about mass percent of solutions, but mass percent could also be used for, say, how much gold is in this ore? So many grams per 100 grams of gold in the ore. That would be solid. So you can use the same expression for solutions or for solid composition. What's the mass percent glucose in a solution made by dissolving 5.5 grams of glucose in 78.2 grams of water? 5.5 grams of sucrose in 78.2 grams of water. Well, mass percent is based upon the total mass. So we have to add those together to get the denominator. 83.7. Now we can put the solute here times 100 and find out what our value should be. So that's
This is one I don't understand as much. I'm getting it now.
6.6%. What is it?
This one, I've just never heard of that before. By mass. Weird.
Yeah, it is. You can think of it as filler. Probably never use it again. 6.6%. Mole fraction. Now we will see this one again. Mole fraction is used a lot with gas composition. Well, that's enough said about that. Okay, so this phosphoric acid was made by dissolving 8 grams of H3PO4 in 100 milliliters of water. Calculate the mole fraction of H3PO4. Okay, this is a little more complicated. So if we're going to say mole fraction of H3PO4, what we need is moles of H3PO4 per moles of H3PO4 plus moles of water, right? Total moles. Okay. So we've got 8 grams of H3PO4. We can calculate the moles of that pretty easy. 8 grams. What's the molar mass of H3PO4? Well, let's see, we got 3.03 for the hydrogens. Phosphorus is what, 32? No, 30. 30.97. And 4 oxygens is 64, right?
Yeah.
Okay, so we got that. Carry the 1, 8, 9, 98. Into 8. So that's 8.16 times 10 to the minus 2. 8.16 times 10 to the minus 2 mole of H3PO4. Let's put that in the denominator as well. 8.12 minus 2 mole plus moles of water. We've got 100 milliliters of water. We don't have any conversion from milliliters to moles for water. We've got to have grams. That's why they gave us density. So 100 milliliters of water is 100 grams of water. Okay, so now we got 100 grams of water. And remember the molar mass of water? 16 plus 2.02.
Yeah. I'm bad at remembering, but I should have.
That's 5.549. 5.5. Probably not going to make any difference with this added to it, but we'll do it anyway. So if I add these two together, that's in the denominator, and then in the numerator, 8.16 minus 5. Mole fraction. All right, we're going to want this in standard notation. It's 1.45 times 10 to the minus 2, or 0.145. That should be the mole fraction. Okay? Took a little doing, but if you start from the definition, then you know what you're looking for.
Yeah.
All right. should have seen this board this morning when I came in.
Bad.
I had to dish out some ethanol and wipe it down. I couldn't get it off with water. Okay. Now we're down to molality. I'm going to try a problem with molality. A solution of phosphoric acid was made by dissolving 8 grams of H3PO4. Well, that was the same amount as before, wasn't it? I'm sorry. This is molality, not mole fraction. And 100 mils of water. Calculate the molality of the solution. Okay. I guess I'm going to have to start from scratch again. So molality is moles of solute, kilogram of salt. Okay. So we got 8 grams of phosphoric acid, and we need grams down here, moles here. So I got to add phosphoric acid again. 3.03. Phosphorus is 32, was it? No, 30. 30.97. Keep saying 32. That's slightly. And 64 for oxygen. 98. There we go. And this is 8.163 times 10 to the minus 2 moles. 8.163 times 10 to the minus 2 moles divided by kilogram of solid. So if we have 100 milliliters of water, that's equal to 100 grams of water, which is how many kilograms?
What do you say?
How many kilograms is 100 grams? One, two, three. There we go. So now we put 0.100.
We've only been out for like a month, but I'm.
Huh?
So we only been out for like a month, but I'm rusty.
Yeah, I know what you mean. 8, let's see, I already got that. Then I need 0.1 divided into that. Okay, so our molality is actually 0.816 molality. Okay? All right. Now we're going to talk about what's the prevailing theory of how solutions form. You think it get more complicated? Yes, again. When a liquid solution forms, then we're going to use that as our basis, but this can be extrapolated to other types of solutions. 3 processes take place. All right, you've got the solute in this step, and the solvent in this step, and then this represents the solution. In this step, we have to add energy. This is endothermic, to separate or overcome the intermolecular forces between the solute molecules. Separate the molecules. So that's an energy expenditure. We have to put energy in to get those things apart. The solvent, we have to do the same thing. We have to add energy to separate the molecules. Then we take these separated and put them together, and this is exothermic. We get energy back when these two interact with one another. They come closer together, they form their bonds. They're intermolecular bonds, and this is bonding between solvent and solute. Okay? That's basically what that says. And this is another way of expressing it. If we say this is delta H1, this is delta H enthalpy 2, and this is 3, then when you add them all together, you get the overall heated solution. So we're saying delta H1 plus delta H2 plus delta H3 equals delta H of solution. So we know that solutions, when we form solutions, they can either get hot or they can get cold, usually. They rarely just stay the same temperature. The reason they get hot or cold is a balance of these values. So if we put a lot of energy in here, a lot of energy in there, and you only get a little bit back, it's going to be cold. But if you put a little energy here, a little energy there, and you get a whole lot back, it's going to be hot. So that's the Broadway version. Okay, and you can actually see that difference in the hospital setting. When you have the cold packs and hot packs, you're dissolving a different compound for the cold pack and another compound, a different compound in water for the hot pack. Okay, I don't think we need to beat that horse. It doesn't say anything more. This is just the way it looks in an energy diagram. If you see, for this one, we put energy in for the separating the solvent and the solute molecules. We put this much energy in, but we get a whole lot back. That means that the net is this decrease here. That's a negative value, which means exothermic. Whereas if you put a lot in and you only get a little bit back, then you get this positive green arrow, that's endothermic. Okay, so let's see if we can make sense of why oil and water don't mix. Use that as our jumping off point. Oh, okay. I thought I was going to get an explanation. But let's go ahead and go to the next one to answer that, oil and water. All right. So think of the polarity of the solute and the solvent. You can have a polar. See how they arrange that. You have solute, solvent. Okay. We can have both of them polar. We can have both of them non-polar. Non-polar. We can have a polar solute, a non-polar solvent. Or we can have a non-polar solute and a polar solvent. This would be oil and water. Oil is non-polar. Water is polar. So let's see where that one is. Non-polar, polar. The second one down. Okay, typically, non-polar solutes or solvents don't take much energy to move the molecules apart. Because what forces do they have available to them? They don't have dipoles. They just have London dispersion forces, which are very weak. Right? So just a very little bit of energy is required here, small energy. But this one requires a lot of energy. So this is small delta H. This is large delta H. Okay, to get those apart. Now this would be delta H1, delta H2. How about delta H3? Right, for the solution. When you bring these together, once you get them apart and bring them together, what kind of interaction are you going to have between nonpolar and nonpolar? You're going to get a very small And this is a small positive delta H, a large positive delta H, and a small negative delta H, very small. So you're not getting any energy back. You're putting a lot in, but you're not getting any back. And what that means is that it's not likely that the solution is going to form because there's no interaction between the molecules. And so once you get them apart, it really doesn't matter because they're not going to like each other anyway. So oil and water don't mix. Let's see, do we have another problem? One factor that favors a process is an increase in the probability of the state when the solute and solvent are mixed. So if there's a significant interaction of the solvent and the solute, then you're more likely to get a solution formed. So this nonpolar polar or polar nonpolar, so this one's going to be large, and this one's going to be small, and this one's going to be small. So you've got small delta H for the solution for either one of these. For this one, you have large delta H positive. You have a large delta H positive for this one. Just getting those molecules apart. But once they're apart, they come back together and give you a lot of energy back. So this one is large delta H negative. That favors a solution. The other possibility is the nonpolar, which is, in our example, is the third one down. So for this one, here, you're going to have a small here, not much energy put in, not much energy put in, and not much energy back. So there's not much difference between these three solutions, three processes. And the interaction is about the same as it is in their separate components. So they're going to form a solution also. If this is similar to these two, and this is similar to this one, then you're likely to get a solution. But if these are radically different from one another here, you're not going to get a solution. And the rule of thumb is like dissolves like. Nonpolars dissolve nonpolars, and polars dissolve polars. Okay, so effects on solubility. Let's look at that now. How soluble is a solute in a solvent? We just talked about the polarity effects. Those are definite effects. And that will occur with virtually any type of solvent and solute interaction. Pressure effects only occur where the solute is a gas. If you have two liquids together, pressure has no effect on it. If you have a solid and a liquid, or a solid and solid, pressure has no effect. It only affects gases. And there's a law that governs that. It's called Henry's law. We're going to see that in another slide. Then there are temperature effects that generally affect the formation of an aqueous solution. In general, solids are more soluble in water if the temperature is increased. But there are exceptions, and there's really no explanation for why. It's just empirical. Let's take a look at some of those things. The structural effects have to do with the polarity. Hydrophobic we call water fearing. So I think what the authors are now doing is focusing on water as the solvent. So we're going to try to stay with aqueous solutions. Hydrophobic literally means water fearing.
Hydrophilic is water loving.
Water fearing are non-polars, water loving are polars. Just that simple. The pressure effects here, this is Henry's law. The concentration of the gas in the liquid has a constant multiplier times the pressure. So what that means is it's different for every solvent-solute combination, but it does vary with this relationship. So K has to be either empirically determined, or we have to use that trick that we use with the gas laws. So we would say, let's solve it for K. K equals C over P. All right, so if this is 1, and this is the initial condition, and then this is the final condition, right, then we can get rid of the K and say, if we know the concentration before at this pressure, and now we increase the pressure to this value, we can calculate the new concentration. That would be the before and after type. So that's why when you buy a bottle of pop and you crack the lid, it goes because you're letting off the pressure. As long as there's pressure inside that vessel, that CO2 remains dissolved in the pop. When you let the pressure off, then it equalizes again, and some of that pressure is released. There's a temperature effect there also, and we're going to get to that in a second. This is the graphical visualization of what's happening. When you increase the pressure from left to right on those gas molecules, you're increasing the frequency of impacts of the gas molecules on the surface of the liquid. And that increases the frequency of movement from the gas to the liquid phase. This is an offshoot of the kinetic molecular theory of gases. More impacts means more solubility. Just like when you compress a gas, the pressure increases because there are more impacts per unit area. Okay, here are the temperature effects. And this is for aqueous solutions in particular. Well, those first two bullet points I already told you about those. Normally, solids are more soluble with temperature increase in water. But there are some cases where that's the other way around. And predicting them is difficult, if not impossible. However, solubility of gases in liquids decrease with an increase in temperature. So what's happening? Well, if you've got a liquid, and you got gas molecules up here, let's seal it off. And you got at one temperature, you got so many of these down here in the liquid. But what happens when you increase the temperature of the liquid? Temperature is the average kinetic energy of the molecule, right? So you're driving the solvent molecules faster, and they're impacting these gas molecules, which gives them more push to get out of the solution. Yeah. So when you increase the temperature, increase the temperature to the next temperature level, there's too much kinetic energy in the liquid for the gas to stay dissolved. So they move out. So that's why gases are less soluble with an increasing in temperature. And you can see that as a practical matter. If you've ever been to a picnic and you've got bottles of pop sitting over there on the hot bench, but you have ice, right? You can pour them over the ice. As soon as you open that bottle of pop at those temperatures, like 80 degrees outside, whoosh, you lost almost all your gas. The fizz is gone. So you pour it on your ice and you've got just syrup water. So that's why at home, I take my pop and I stick it in the refrigerator first. Then when you crack it, it goes, and you got most of your fizz still in there. because it's at lower temperature. Another example is if you boil water on the stovetop, you're going to boil some eggs or you're going to make spaghetti or something, pasta. When you first start heating it, and the first bubbles that you see are not water vapor. Those are gases coming out of solution. Because when you heat it up, they can't stay dissolved. So they come out, and then after that, you'll start getting phase change from liquid to gas. These are examples of solubility of various solids in aqueous solution. And you'll notice as the temperature goes up, sucrose becomes more soluble. Another example, potassium nitrate becomes a lot more soluble. Sodium nitrate some. Sodium bromide, almost no difference, just slightly. Potassium bromide increases. Potassium chloride increases. But sodium sulfate and cesium sulfate, I think that's right. No, cerium sulfate, Ce. Cerium sulfate go the other direction. They become less soluble as we increase the temperature. Gases, you'll notice that as you increase the temperature, the solubility of methane goes way down. Oxygen goes way down. Carbon monoxide, nitrogen. Helium changes very little. In fact, helium is almost insoluble in liquid. You don't get much helium in solution at any temperature. So when we were running high pressure liquid chromatography, the process.
When you were doing it in school or when we were?
Research. Yeah. You'd have a column, and it would be packed with some beads, some filling, right? And you would want to inject your sample here into a moving, we call it mobile phase. A mobile phase, and this is the stationary phase. And it would run through here, and as it did, it was carrying along the dissolved analytes that we were interested in separating. All right, so the way they separate is some of them are more strongly attracted to the stationary phase than they are to the mobile phase. So they stay here longer, and they lag behind. And the ones that don't care much about associating with the stationary phase, they get moved on down the line. So that separates them into different bands. Well, this is very high pressure. And if you've got any gas dissolved in that mobile phase, when it comes out the other end and the pressure is off, atmospheric pressure is released, that gas comes out of solution like nobody's business. And two things could happen. It could mess up your detector where it wouldn't work properly, or it could damage the detector. So what we want is very low gas soluble in this mobile phase. Now there are a couple of ways you can do that. You can draw a vacuum on your mobile phase before you use it. You know, it sucks all the air out of it. Any dissolved gases are gone. That takes a long time. So what we used to do was we would have our bottles of mobile phase here, usually 2 or 3 of them because they combine and the pumps would combine them the way we wanted them to. And what we would have was a line in here with a centered, what do you call those things in the aquarium? That you blow your air through and it makes tiny bubbles.
I know what you're talking about.
Yeah, we would have the same type of arrangement here, right? So it would blow in here a gas that was very insoluble, helium. We would use helium. Helium would displace all the other gases. Nothing left but helium. We'd sparge it for 15 minutes. And that would alleviate the problem of pressure release at the other end because there wasn't that much helium in it anyway. All right, enough of that. Okay. What would happen to if we had a solution, an aqueous solution next to a pure water solvent in this bell jar. Well, you're going to have water molecules, and of course the solute is not volatile. So maybe it's salt or some other compound that would not vaporize. So the only thing that can go into the vapor phase is water. So inside this enclosed container, you've got water molecules that are moving into the vapor phase. Well, what you observe is that the water molecules from the pure water at the surface, you've got more water molecules at the surface working their way into the vapor phase, and they're at the same temperature. Whereas in the aqueous solution, you've got these non-volatile molecules in the way. They're holding the water molecules down, they're attracted to them, plus they're just steric interference. There's not enough space for the water. So you have more vaporization from the water, pure water, than you do from the solution, and you see a migration of water molecules from the pure water to the aqueous solution. And if this aqueous solution is concentrated enough, then you can have all the water sucked out of one into the other, and they're never touch one another. This works really well if you have a concentrated sulfuric acid solution on the solution side in pure water. It'll happen really fast. Okay, now we talk about vapor pressure. What is vapor pressure? If you have a closed container and you have a solvent, let's talk about pure solvent first. You have a pure solvent down here, and you seal it off. Then the first thing that happens in that space is you get solvent migration into the vapor phase. Okay? And there's no return. But eventually you get enough solvent molecules into the vapor phase that they start returning. And you reach a place now where it's at equilibrium. Okay? When it reaches that equilibrium where the vaporization and the condensation are equal in rates, then you can measure a pressure here. You measure pressure in this space at a given temperature. It's temperature dependent. And that's the vapor pressure for the pure solvent. Okay? Now, if you put non-volatile molecules, like we had in our previous example, non-volatile molecules down here, then they interfere with the vaporization phase, movement into the vapor. So the measured vapor pressure decreases. Okay? We can quantify that with Rayleigh's law. And if you want to know the vapor pressure of the solution, then you need to know first the vapor pressure of the solvent. Okay? And then multiply that by the mole fraction. Oops, did that wrong. The mole fraction of the solvent itself. So if you know the mole fraction, so it's going to be less than it was in pure. Pure is going to be mole fraction of 1. Mole fraction with your solvent in there, your solute, is going to be less than 1. So that means that the pressure of the solution is going to be less than the pressure of the solvent. Multiply that by that fraction less than 1. Well, most of the time, we calculate the mole fraction of the solute. So it's like I said before, the mole fraction of the solvent is equal to 1 minus the mole fraction of the solute. So if you know the mole fraction of the solute, you can calculate this value from there. Now that's if your solute is non-volatile. And there are many, many examples where both the solvent and the solute are volatile. So now we have to modify Raoult's law to accommodate. All right, so here's what it would look like. The vapor pressure of the pure solvent is mole fraction of 1 on the right-hand side. So that would be the pure. And then as the mole fraction of the solvent decreases, we get a lower and lower and lower vapor pressure. Here's what it looks like if you have modified Raoult's law. So might as well write it that way. And this is an example where you have two, a solvent and a solute, and both are volatile. So the total pressure in each one is actually a combination. You can work from the vapor pressure of the pure A component, and really at this point it doesn't matter which one's the solvent or which one's the solute because they're both volatile. So the A component is combined with the B component, and these are the pure vapor pressures. So what you need to know then is the mole fraction of A in that mixture and the mole fraction of B in that mixture. And then when you add those two together, you get the total pressure. Okay. Most solutions, not all, let's just say many solutions don't exhibit ideal behavior. And the next slide should show you what the difference between ideal and non-ideal behavior. So if you look at this graph on the left, you've got, and you watch the partial pressures of A and B individually with their mole fractions. So if A is going up like this, let's see, we're going to, mole fraction of A is increasing to the right. So its pressure is going to show, all right, if it's 0 here, of course, it's going to go up like this until it reaches 1. And then if we've got a solution, then we're looking at the mole fraction of B increasing to the left. So it's going to be 0 on this end, and it's going to go toward 1 mole fraction on that end. Okay? So based upon this expression, if we add the actual pressure, which is any point on these lines, actual pressure of both of them, we're looking at this one plus this one, which would be somewhere up here. Right? And you can do that all along there. And if it's ideal, actually all you have to do is connect these two lines. And that would be the vapor pressure total. Right there. That would be an ideal vapor pressure solution. Now, non-ideal can come in two varieties. One is where there is actual either a weak solute-solvent interaction or actually a repulsive interaction where they repel one another. And in that case, you're going to get a deviation like this, right? Positive and positive. And then when you add those together, you get a positive like that. Oh, excuse me. No, I went the wrong direction. Sorry. Let me start over again. If you get a weak interaction between the two, or repulsion, then you should. No, that was right. That was right.
I thought so.
Yeah, they changed. Okay. I thought the dotted line was added to the solid lines. No, they changed the solid into the dotted lines, and then the solid lines are the new case. All right, so eventually you get a positive interaction. You get positive value there, and this would, I'm going to use dotted lines instead. This would be the effect. And notice that when the mole fraction of one is very, very small compared to the other one, you approach ideal behavior. This is for a weak interaction or repulsive interaction. If you get strong interactions between the two, then you're going to depress the vapor pressure of each other because they're holding each other back from going into the vapor phase. So then you would get a negative here and a negative here, and this would be negative for strong interactions. Things like, I don't know, water, alcohol. They both have hydrogen bonding available. So they would hold each other back, and their vapor pressures would be less than ideal. Here we go. Let's see. Oh, we've got some examples. Okay, good. This is an ideal solution, benzene and toluene. Benzene and toluene are very similar in structure. They're both nonpolars. Benzene is this hexagonal shape with, it's an aromatic compound. Toluene is almost the same. But it has a methyl group on the side. Right, so it has no polarity whatsoever. There's very weak interaction, if any. So it's ideal. They have no impact on each other. Acetone and water, the deviation is negative because acetone and water both have, I wouldn't say acetone has hydrogen bonding, but it does have a polar character. Right? We know what water looks like, right? So it's polar like this. Acetone is double bonded oxygen and then methyl group here and methyl group here. So there's some polarity here with this bond, and that gives it a slight polar nature. So the interaction between the two has that polar attraction. So the negative behavior for acetone and water gives you this deviation here. Now for ethanol and hexane, they don't like each other. They're soluble in one another, ethanol and hexane, but they still repel one another because ethanol has the hydrogen bonding available. Hexane is completely nonpolar. All right. Let me make some room here. Oh, we're running out of time. Oh, okay. 3 o'clock is when lab starts. Okay.
We got lab today?
Well, we may want to talk about it a little bit. Do some prep. I'll just leave that there for now. Okay, for each of the following solutions, would you expect it to be relatively ideal with respect to Rayleigh law, or show a positive deviation or a negative deviation? Well, let's look at what we got. Hexane and chloroform. Chloroform should be polar, even though slightly polar. So I would expect a positive deviation of hexane and chloroform. In other words, they repel one another. Ethyl alcohol and water have very strong attraction. They should be a negative deviation. Hexane and octane should be, they could care less. Right, they're ideal. Now let's see, is it going to, it didn't give the answers. Okay, so take my word for it. Now let's talk about colligative properties. A colligative property is a property of a solution which does not depend on the nature of the solute, only the concentration of the solute in the solvent. So we could put we can make a 1 molar sugar solution or 1 molar, let's see, I guess you could say salt, say half molar salt solution because it splits into 2 parts and makes a molar. And they would behave exactly the same way as far as how they affect the freezing point of water, the boiling point of water. That's why ice cream freezers work. When you mix a lot of salt with water, the freezing point of water goes way down, way negative. And that's enough to freeze your custard. The reason it does that is because the freezing point of water is depressed as the concentration of salt in the water increases.
That why they say not to put, people for a long time are burning their clothes, but like they'll put salt on their hands. The ice. Have you heard that?
It would,
You
yeah.
know, it ate their skin up. Stupid, but people are doing it like crazy.
There are 2 possibilities there. One is that would be super cold and you could frostbite your hand. Yeah. Or you could increase the ionic concentration at the surface of the skin and damage it that way.
Yeah, there was a lot of like.
But it's probably a combination.
I never heard that before. I didn't know why.
So these 4 colligative properties we're going to look at. One is boiling point elevation. So as you increase the concentration of the solvent, you increase the boiling point of the solution. So when you put salt in your water before you throw the spaghetti in it, that spaghetti is being boiled at a higher temperature than it would be with pure water. Freezing point depression goes the other direction. As you add more solute, then the freezing point of the solution decreases. That's why you can throw salt on the road in the winter and melt all the snow down to a certain temperature. Right? It'll up to a certain concentration. The air temperature can go down to a certain level, and the salt will still work. But below a certain temperature, they call it the eutectic point, then it won't work anymore.
I just learned that because I was throwing salt everywhere on my driveway because I was trying to get out small. Like, after about 20 degrees, it don't work.
Yeah.
I was like, really? And I didn't realize.
Now that's for sodium chloride, table salt.
Yeah.
If you buy the other type of salt, I forget what they call it. It's a mixture. The type I bought this year was a mixture of calcium chloride and magnesium chloride. It works to a lower temperature, and it doesn't damage your concrete either. Sodium chloride will eat holes in the concrete.
Yeah.
I learned that the first winter I was here, and I was out there in the spring patching holes. But another colligative property of solutions is osmotic pressure. In other words, as you increase the concentration of the solution, you increase its osmotic pressure. And that is to say that, for instance, if a salt solution surrounding a cell is greater than inside, which way is the water going to move? It's going to move out of the cell. And if it's less concentration outside the cell, water's going to move in. Vapor pressure is another colligative property. The vapor pressure will change based on, as long as and this is a takeoff of Rayleigh's law, as long as the solute is non-volatile, then you can change the vapor pressure based upon the molar concentration of the solute, and it doesn't matter what it is. Now, it does matter what the solvent is, and we're going to learn how to use that information in just a second. Okay, let's talk about boiling point elevation first. We're also specifying that the solute is non-volatile. It works for volatile solvents, but since the solutes, if the solute is volatile, then as you increase the temperature, then you're going to also drive off some of the solute, and that changes the concentration. So it's kind of defeating your purpose. So we're going to discuss it in terms of non-volatile solutes. What does it do to the boiling point elevation? Well, we're looking for a change in temperature. That is, what's the difference in temperature between the pure solute, the pure solvent, pure solvent boiling point, okay, versus the boiling point of the solution. So we're looking for a difference in temperature. That means if you're going to do an experiment, you got to do the pure and you got to do the solution and find the boiling point. Then do the difference in temperature. Okay, this was related to the concentration of the solute by a proportionality constant, which is particular for the solvent. So water will have a value for it. We're going to use benzoic acid and lauric acid. So I think lauric acid is the solvent. Lauric acid will have a value, a K value, for its. Now we're not going to do boiling point. We're going to do melting point. But it's a similar situation. And then we need the molality of the solute. And that's because we're looking at a difference in temperature. We can't use molarity because molarity will change with temperature. Molality will not. Okay, so the change in, this is change in boiling point temperature. Change in melting point will have a K value, and then it will also relate to the solute concentration and molality. That's on the next slide. Freezing point depression. Now, up to this point, I've been a real stickler about the sign, like final versus initial, and you have a sign. In this case, you just need the absolute value. What is the difference in the temperature? You don't care about the sign. You know that with the boiling point, the final temperature is going to be higher than the initial. But with the melting point, the final temperature is going to be depressed. It's going to be less than the initial. But we only want the absolute value. I should have put that in the slide, actually. We'll talk about how to use that to find the molar mass when we look at the lab. Okay, we'll come back to that. So this is what a pressure versus, let me hide this thing. Yeah, pressure versus temperature for the boiling point and freezing point of water. Let's see. So we're trying to describe both of these in the same diagram. A difference in boiling point here. So we see that the solution is in the blue line. The red line is pure water, and the blue line is the solution. So what we're seeing is we reach, let's see. Let's go to the boiling point first. Boiling point of water at 1 atmosphere pressure. Okay, so that's important. If we're at 1 atmosphere pressure and the water's boiling, then it'll happen at this temperature. But if we make a solution out of it, then what we find is we actually decrease the pressure, the vapor pressure of the water, and that is a determining factor for the boiling point. Right, the vapor pressure has to exceed atmospheric pressure, and it means that we have to get the solution hotter in order to reach the 1 atmosphere vapor pressure. So that's why the boiling point increases. Now, let me see if I can explain the freezing point. What? Okay. Yeah, go ahead. Yeah, it's recording. Let's see, freezing point. So this is the freezing point of pure water, and the freezing point of the solution is lower, but the reason for it is not as self-evident as the boiling point. Pressure is less for the freezing. Okay, so our vapor pressure is dependent upon temperature, and as you decrease the temperature for the pure solution, then you get a freezing point here. But in order to freeze it with a solute involved, You have to decrease the temperature even further to get that. The pressure drops because you've got a solute in there. Yeah, because you have the solute in there, the pressure is less for a freezing point. Okay. That's not as pretty as the boiling point, but all right. So here we have an exercise that we're going to try to do. Solution was prepared by dissolving 25 grams of glucose in 200 grams of water. The molar mass of glucose is that number. What's the boiling point of the solution, of the resulting solution in degrees C? Right. And in this case, the temperature is degrees C, or whatever the constant tells you it is. Right? It may say K, but degrees C is going to be the same. All right. What it doesn't tell us is what's the K value for water. So I need to find that. Let's see, where is that going to be? I might have to look it up. Let's see, boiling point. The boiling point elevation constant for water. That's what I'm looking for. Come on. Okay. Yeah, I got internet. I need to put that in there. Come on. Okay. Come on. There we go. Boiling point elevation constant. Let's see. Just add water to that. So okay. Let's see. Oh, it didn't. Where's the value? Let's try this. Ah, here we go. Water. Here it is. 0.512. So the K for water, KB for water is 0.512, and units of measure are degrees C kilogram per mole. Degrees C kilogram per mole. Now, what you may also see is this expressed as mole per kilogram is molality. So you may see it written this way, per molal. It's the same thing. Okay, so now we got that value, which should be here. Excuse me. And the question is, what's the boiling point? So we need to find out what this difference is. First, what's the molality of the solution? We've got 25 grams of glucose with 180.16. Yeah. 25 grams of glucose, and we're going to change it to moles. 180.16, 180.16 grams per mole. And divide that into 25. That's 0.1387 moles. That's moles of the solute. And what's kilograms of the solvent? 200 grams of water. This is in 0.200 kilograms of solid. So we can find the molality there by dividing 0.2 into that thing. So that's 0.6938 molal. Okay. So now we've got this value. The delta T then is equal to 0.512 degrees C per molal times 0.6938 molal. So the molals cancel, and we have our temperature difference there. 0.512. And our temperature difference is 0.3552 C. That's the difference in temperature for boiling point. So that the boiling point is elevated by that much. So the boiling point of the solution is going to be 100 plus 0.355, or 100.36. Okay, not much. Okay. All right. Now, here's the fly in the ointment. The Van Hoff factor. Let's see. I don't want to erase that. It's still, that's still in my phone. So I can erase this. The Van Hoff factor is a correction factor. That's usually empirically determined, but it follows a pattern. If you dissolve a solute that you know it will not dissociate in solution. In other words, when you put 1 mole of it in solution, 1 mole is there in solution. Then your Van Hoff factor is 1. So the Van Hoff factor goes right here. Okay? If you put something in solution that you know is going to dissociate into 2 moles of product, like sodium chloride, when you put that into aqueous solution, you get sodium ions and chloride ions. Then your Van Hoff factor will be 2. Or if you get calcium chloride, like our special salt, and magnesium chloride, actually, either one. I got a mixture that I throw out on my icy wall. This produces 3 ions for every mole of it. So our Van Hoff factor there is equal to 3. Now, that was the fly in the ointment. Now here's the fly in the fly. When you have ions as part of the reason for the Van Hoff correction factor, sometimes, and this is empirically determined, you can't reason it, you get ion pairing. So we might think that, for example, the Van Hoff factor we think would be 3 for this molecule. But if you get calcium and chlorine combining, so that would be a +1, or calcium and 2 chlorines, that would be neutral. That decreases the number of ions in solution. That ion pairing decreases this value. So instead of 3, it might be 2.8, something like that. And that there are reference materials that will tell you what that value is for different solutes at different temperatures and for different concentrations. Because if you increase the concentration of your solute to a very high level, you're going to increase the probability of forming those ion pairs. Right? And that's beyond us here. Just be aware of it. Theoretically, then, sodium chloride would be I2, calcium nitrate would be I2, because the nitrate ion is polyatomic and it holds together as a single ion. And sodium phosphate would form 3 sodiums and 1 phosphate, I would be 4. That's a good statement. In fact, I just made that one. Ion pairing is most important in concentrated solutions. So if your solution is dilute, then you can ignore ion pairing. Ion pairing most dilated. Yeah, and ion pairing is most important for highly charged ions. So it's 2+ and 3+ ions. Like aluminum chloride, probably the ion pairing probability would be very high because it's a small ion with a large charge on it. So there's your modified equation, and that works for either boiling point elevation or freezing point depression. Okay, let's see. Ooh, this is gonna, did I work that one out? Okay, 20 grams of sucrose and sodium chloride mixtures dissolve in 1 liter of water. Okay, so you got a mixture of sucrose and sodium chloride, but you don't know what the ratio of the two is. You just know the total value is 20 grams. Dissolve it in 1 liter of water. The freezing point of your solution is found to be 0.426 degrees C. So you depressed, the delta T is 0.426. 0.426 for that. And then we need a value for freezing point, melting point, freezing point, same thing. What's the mass percent composition of the original mixture and the mole fraction of the sucrose in the original mixture? Okay, this is a very complex problem. I think that's why I went ahead and worked it out in the slides.
I was gonna say it's already like that.
Yeah, come on. There it goes.
Will we do any like that?
If you did, there'd probably be extra credit anyway. We've got the total mass of the solution, that's given. We've got the freezing point as minus 426. We're going to let the mass of the sucrose equal X grams. That means the mass of the sodium chloride is 20 minus X. So we're using some algebra here. If we want the number of moles of sucrose, then we divide X by 342.34 grams per mole. So that gives us the moles of sucrose. And the moles of sodium chloride is 20 minus X divided by its molar mass, 58.45 grams per mole. So the molality of the solution then is this one, the moles of sucrose, plus the moles of sodium chloride divided by 1 kilogram. That's the molality of the solution with X as our unknown. Okay, moles per kilogram. Oh, okay. So in this one, the Van Hoff factor for sucrose is 1 because it doesn't dissociate. The Van Hoff factor for sodium chloride is 2. So the molality of the solution, that's the actual molality of the solution, but we have to incorporate the variation in their dissociation in solution. So this is the freezing point depression constant for water, 1.86 degrees C per mole out. And the difference in temperature, the change in temperature is 0.426. So that's what we're going to put in this equation. This is 0.426 change in temperature equals the Van Hoff factor times the molality times the K value. Okay. So we're going to solve it for the Van Hoff factor and molality. So we just take this value over here and divide it into that one, and we get 0.2290. Well, 0.2290 is I times the molality. Now here's the trick. When we go from this expression to this expression, we're saying this 0.2290 is a combination of this Van Hoff factor of 1 times the molality of this solution, this part of the solution, and this is 2 times the sodium chloride part of the solution. So that's where we get this equation. Then we solve for X. Just keep going until we solve for X. And X turns out to be 14.55 grams of sucrose. That means the remainder, 5.45 grams of sodium chloride. So the mass percent we calculate as 72.8% sucrose, 27.3% sodium chloride. But it also wanted mole fraction. So this is the mole fraction of the sucrose. Right? This is the moles of sucrose. Right? We got the grams of sucrose, and we got the total moles. So we have to take the grams of sodium chloride and make moles out of that. And the end result is 0.3131 mole fraction of sucrose in the original mixture. We went way around the barn to get that one. Okay. So let's take this real world example. A plant cell has a natural concentration of 0.25 mole. Yep. If you immerse it in an aqueous solution with a freezing point of minus 0.246, will the cell explode, shrivel, or do nothing? Well, what we're saying is, what's the concentration of the cell versus the concentration outside the cell? And we have to find out the mole concentration outside the cell with this freezing point depression value. So we take that freezing point depression value and we use our freezing point calculation to determine that the molality outside the cell is 0.132. Compare that to 0.25. It's less outside the cell, so what's going to happen? You got more water outside the cell than you do inside, so water's going to move in, and eventually the cell will explode. There we go. Water will move into the cell because the concentration, you can look at it two ways. The concentration of the solute outside is less than inside. Or you can say, based upon those concentrations, what's the concentration of water? Concentration of water inside the cell is less than it is outside the cell. Right? And water is the only thing that's going to move through the membrane. So if the concentration outside the cell is higher, it's moving in and the cell will explode. All right, osmotic pressure. Turns out osmotic pressure is not dependent upon, well, it is dependent upon temperature, but the formula already incorporates temperature into this constant. This is our ideal gas equation, ideal gas constant. So it incorporates in there a temperature. So any temperature that we have for this value is canceled out with that R. So using molarity is okay, because we've already compensated.
What is that sign called?
That's a pi.
That is a pi?
Yeah.
Because on there it looks funny, but you wrote it like a pi.
Yeah, pi r squared.
Okay.
That's the area of the circle.
On there it looks like a.
Oh, yeah.
A 3/4 square, so I didn't know.
That's a different font.
Okay.
Yeah. It stands for osmotic pressure.
Because I wrote it out, I didn't want it to look like a pi.
Okay. Let's see. This is what we're trying to explain is where the idea of osmotic pressure comes from. If you've got something down here like that, submerged in liquid, and this is a membrane. Right? So water can cross that membrane, but nothing else can. This is a semi-permeable membrane. When we say semi-permeable, we're implying that the membrane will only pass water and gas molecules. So in here, we have pure water. And in here, we have a solution. So which way is the water going to move? It'll go that way. Right? And it's going to go that way. as long as the pressure of the returning water or the rate of the returning water is less than the water moving in. And it's going to keep rising, rising, rising until the difference here, this pressure is high enough so that now the return rate is equal to the inside rate moving in. Once those are equal, then this difference in pressure is the osmotic pressure. All right, one second. I think I missed it. Missed a dose of medicine. Yeah, I did. Take this one now.
Starting to not feel good again.
Yeah, it's tough. It's a. The doctor said it was probably an infected hair follicle, and
Is it in your nose?
yeah, it started right about here, and it just spread.
You like making your nose throb, or is it causing congestion?
No, it makes it. I can feel my pulse.
Really?
Yeah.
Oh, Lord, that's awful.
Not now. I did last night, but it's better now.
Oh, well, you mentioned, I was going to say it probably causes your headache. But
Yeah, it does cause a headache.
it's so odd that could.
But I looked up some information on it, and the most common bacterium that's resident in your nasal passages is a staphylococcus, and they're just ripe and ready for an invasion. Right, so if a place opens up, they're going to move in and multiply. I don't know if it's MRSA, but it is staph probably. Okay, so that's an explanation of osmotic pressure. This is another way of looking at it. If you have the pure solvent on our left-hand side and the solution on the right, of course, solvent's going to move into the right-hand side until the pressure from the right-hand side is high enough to cause to establish an equilibrium of movement of the solvent molecules. Okay. And this also is subject to the Van Hoff correction. So we stick an I in there for the Van Hoff correction. So if you have 1 molar sodium chloride solution, then you need to put 2 there. Either that, or when you calculate the concentration of ions, you just take that into account and say, okay, the ionic concentration is 2 molar instead of 1. All right, let's see. We have 33.4 milligrams of a compound dissolved in 10 milliliters of water at 25 degrees. Solution has an osmotic pressure of 558 torr. Calculate the molar mass of this compound. Okay, let's see. Did I work it out? Or do I need to do it from scratch?
You worked it
Oh,
out.
good.
Okay.
Did I? Yeah. Okay, so our universal gas constant is the 0.08206 because it has pressure in it, atmospheres. It has moles per liter, which is molarity. And then the temperature is canceled out in the calculation. So we need pressure in atmospheres. That's the first thing. 588 divided by 760 is atmospheres, gives you the osmotic pressure. Okay, and then the molarity is the unknown. Gas constant is there, temperature is there, and the temperature has to be in Kelvin because the gas constant is Kelvin. And we come out with a molarity of 3.164 times 10 to the minus 2 mole per liter. Okay, that's only part of the way to this solution because the question is, what's the molar mass? Okay, so this is moles per liter. The let's see, are we given volume too? Yeah, 10 milliliters of water. The compound is dissolved in 10 milliliters of water. So what we want to do is use this molar concentration to determine what are the actual numbers of moles of the compound. So the molarity is determined here times the liters of the solution, which 10 mils is 0.010 liters. And we've discovered that the moles of the compound or the substance is 3.16 times 10 to the minus 4 moles. Right? And we didn't even have to know what it was. This told us how many moles there were without knowing. Remember back when we did empirical formula, and then we moved to molecular formula? We had to know the molar mass of the compound. This is one of the ways to find it. So we got that many moles, and we're told that the sample we dissolved was 0.0334 grams. So we divide that by moles, and we get 106 grams per mole. That's the molar mass of our compound. And then we could take that back to the empirical formula and determine the molecular formula from that. All right, this was a fun project that I worked up to this slide. When I was a kid, probably strange, but I wondered why 250, 300 foot tall sequoias in California, how did they get the water that high, those leaves, right? Because we were studying in school that air pressure would only raise water about 33 feet if a vacuum was pulled above it in a tube. That's as high as it would go with atmospheric pressure pushing, right? So it couldn't get to the top by that. Well, somebody suggested that, well, maybe it wasn't not a push, but a pull, right? Because you can draw water up with a pump, or you can suck it in a straw and it'll come up. So maybe instead, we're not just making a vacuum up there, but we're actually pulling the water once it's, well, if the tree's really small, right, it's going to make it with atmospheric pressure anyway. So as it gets taller, you still got that column of water, and the water goes into the leaves, and the stomates open and evaporate, and that causes the water behind it to want to fill in the space by, what's the word? No. Shoot. I hate it when this happens. Surface tension. Because it evaporates, you know, and causes the water to go like that because it's losing things, and then the surface tension draws it back up. So is there enough surface tension there to pull it up? Well, it didn't take long for scientists to try that experiment and find out it was pure crap. Right. So the other possibility is still a push. So this is where I went with this problem. In the roots of these trees, the dissolved solids in their sap is sufficiently high to produce an osmotic pressure in the roots of 20 atmospheres in the roots. That's pushing on that water, right? It's drawing water into the roots from the soil because the concentration inside the roots is higher than it is outside, so the water's moving in. And it can produce a pressure, an osmotic pressure of 20 atmospheres. Well, the question is that enough to drive water to the top? Right, so that's what I'm doing here. We're starting 20 atmospheres and a 300 foot tall tree. So if it's 300 feet tall, how many millimeters is that? Right, so this is many millimeters, the conversion to millimeters of the tree height. Then we say, with 20 atmospheres, convert 20 atmospheres to millimeters of water. An atmosphere is 760 millimeters of mercury. But mercury is 13.56 times as dense as water. So the water is going to be pushed 13.5 times further. So that's where this correction factor comes from. And we find out that when we convert that, we find that water can be pushed 2 times 10 to the 5th millimeters high, when it only needs to go about 10 to the 5th. So it can go twice as high as it needs to. So that answers the question.
Can you go 600 feet?
It could go 600 feet, yes. Now, I don't know in Earth's history if we had 600-foot tall trees, that are extinct now, of course. But it could, if they had the same physiology in their roots. That's the other question. Okay. Now we're just going to kind of jump around with some ideas. What's a colloid? We talked about mixtures that are not uniform, or mixtures that are uniform, but they still, well, actually, homogeneous mixtures are solutions. Non-homogeneous mixtures or heterogeneous mixtures are not solutions. But what's a colloid? Well, in a solution, the solute, as we described earlier, breaks apart, the solvent breaks apart, and then they recombine, right? The solvent, you make a hole, and then you shove solutes into it, and they intimately interact. In a colloid, they don't do that. But the colloid does share one thing in common with solutions. Once a colloid forms, it will not settle out. Right? The particle sizes are much too small to settle. The kinetic energy of the dispersing medium, we call it, not the solvent, but the dispersing medium, the kinetic energy is sufficient so that it's banging against the dispersed medium and keeping it suspended. So it's a perpetual suspension. That's a colloid, and it's based upon particle size. So molecules or ions typically are in the size of between 1 and 1,000 nanometers. Let's see, 1 nanometer is 1,000 nanometers is a milli. What's between milli and nano?
Million nano?
Yeah, milli's 1,000, nanos a billion. What's a million? A millionth of a meter. I'm having trouble today. Let's see, millimeters, micrometers. Yeah, micrometer. So it's between 1 nanometer and 1 micrometer in size. Now we have different types of colloids that can form. Some of them are natural and some of them are man-made. Fogs. I drove through a bunch of fog this morning. And a fog has a dispersing medium of a gas, that's the air, atmosphere, and the dispersed substance is a liquid. It's very, very, very tiny drops of water condensation. But they're so small that they can be suspended by the kinetic energy of the dispersing medium. That's known as an aerosol. You can also, actually, that's a colloid that's called an aerosol. Another aerosol is a solid dispersed in a gas. So smokes are aerosols also, airborne bacteria. If we disperse a gas in a liquid, like whipped cream, that's a foam. Or if you shoot insulation into your walls or in your ceiling, that's a foam until it solidifies. And then once you've got a solid and a gas, that's a solid foam. Liquid in a liquid, like milk or mayonnaise, is an emulsion. You know how you, not pasteurize, but homogenize milk to get the fat, keep it from rising? They take the milk and under high pressure, they drive it through these stainless steel sieves with very, very tiny holes. And it goes through and it breaks those fat globules up into very tiny particles, so tiny that they won't coalesce anymore. That's how you homogenize milk in the modern.
I saw that. We didn't really on like what I did there and we didn't watch it.
Okay, good. Let's see. Gelatin. That's a solid in a liquid. So that protein that they extract from animal bones and cow hooves that they make your Jello out of. That's a solid and a liquid. Yeah.
That healthy?
Yeah. Yeah, it's just they extract the protein. It's a collagen.
Yeah, no,
Yeah. Oh, now you're never going to eat Jello again, are you?
it's fine for you, I guess.
Well, it's a type of protein that you don't digest.
Right.
Yeah, there are lots of protein molecules in it, and our bodies don't deal with those. Anyway, marshmallows, gas in a solid, the solid foam, cheese and butter, liquid in a solid, solid emulsion. And the last one, ruby glass, is a solid in a solid. The ruby glass actually has a technological history. That ruby glass was used in the original lasers when, I forget the guys who did that first. Well, the company they were working for, it's faded into history. But they took a perfect crystal of ruby glass and they surrounded it with a fluorescent flash tube. And that at one end, they put a fully reflective mirror, and at the other end, they put a partially reflective mirror. And when they flashed the ruby, it excited the ruby molecules. They emitted light, but when they did, each one stimulated the emission of light from another molecule. And it stimulated that light in the same direction the other one was going. So they bounced back and forth in that environment until the intensity increased to a point it could pass through the partially mirrored surface. And that was your first ruby laser. Coagulation. Coagulation is a process by which a colloid is destroyed. When we mean destroyed, that means you no longer have the suspension. In other words, it drops out of suspension. And you can accomplish it in different ways. It depends on what the suspended medium is made of. Proteins, if the suspended medium is protein, you can either heat it or you can add an electrolyte. You can salt it out, add salt, and it destroys the structure and causes it to actually increase in size versus its mass. And then now the dispersing medium can't hold it up anymore, drops out. That's it.